Hello. So today we're going to talk about two more important theorems in calculus, and those theorems are Rolle's theorem and the mean value theorem. Now, try and remember from the last video that we talked about something called the extreme value theorem, which said that if we had a continuous and differentiable function f of x on any closed interval, that we were guaranteed to have a minimum and a maximum value in the interval. The only problem with the extreme value theorem is that those two extreme values, those extreme points, they could be at the ends of the interval. So what we're going to talk about today is a theorem that guarantees that we get an extrema value on the inside of our interval and not at one of the endpoints. And that theorem is Rolle's theorem. So Rolle's theorem says if f of x is continuous on the closed interval from a to b and differentiable on the open interval from a to b, if we have that the y values at the endpoint, so if f of a equals f of b, so if the y values are the same, then there has to be at least one c value in the open interval from a to b such that the derivative of c equals 0. So that says that if we have a closed interval and the y values of the function are the same at the endpoints, then there has to be at least one extreme value inside the interval. In other words, there's at least one point inside the interval where there's a horizontal tangent line, which means that it's either a minimum or a maximum value. So let's try using this theorem. So let's use Rolle's theorem to determine that if there are any extrema in the interval 1, 2 for that polynomial. So before you can just go on and apply Rolle's theorem, you have to make sure that all of the conditions are being met. So we know that since f of x is a polynomial, f of x is definitely continuous, and it's continuous everywhere. So it's continuous. And since it's a polynomial, it's also differentiable. So we have those two conditions being met. So the third condition that we have to check is that f of a equals f of b. So our a in this case is going to be 1, and our b is going to be 2. So let's find f of 1 and f of 2. Well, f of 1 is going to be equal to 1 squared minus 3 times 1 plus 2, which is equal to 1 minus 3 plus 2, which is equal to 0. Okay, so let's find f of 2, and let's hope that it's going to also be equal to 0. Okay, so now we're going to get 2 squared minus 3 times 2 plus 2, which is equal to 4 minus 6 plus 2, which is equal to 0. So we have that this third condition for Rolle's theorem is being met. So since all three conditions are met, since f of x is continuous and differentiable on the interval, and the y values of the endpoints are equal, so f of a equals f of b, we know that there's at least one extrema value inside that interval. So now we can say by Rolle's theorem, f of x has an extrema value in the open interval. So in the open interval from 1 to 2. And that's our answer. So sometimes with Rolle's theorem, you're not necessarily going to be asked to find the c values. You might be asked to take the derivative and then find at what value they occur at, which we could do. But the whole idea of Rolle's theorem is just that if you meet those three conditions, if you check for all three of them and they're all there, that you definitely have at least one extrema value in the interval. So sometimes that could help you to figure out whether or not you have to do the derivative and solve it in order to determine if there are actually any extrema values. You could use Rolle's theorem and just say, okay, there's definitely one, so it's worth doing all of the work, or there's definitely not an extrema value, so I'm not going to take the derivative and try and solve it. So let's try another example. So let f of x equal x to the fourth minus 2x squared. And let's find all of the c values in the interval from -2 to 2 such that the derivative of c equals 0. So that's not exactly the same setup as the last problem, but again, we can use Rolle's theorem to make sure that we have extrema values in there first before we go and solve them. Because if f prime of c equals 0, that means c is an extrema. So let's use Rolle's theorem first to determine if we have any, and if we do have extrema, we'll go ahead and solve for them. So again, f of x is a polynomial, so f of x is going to be continuous and differentiable. So we can write those conditions up so we can know for sure that they've been checked and that we can apply Rolle's theorem. So the third condition for Rolle's theorem was that f of a equals f of b. So let's find what those two values are and check that they equal each other. So f of negative 2 then is going to be equal to negative 2 to the fourth minus 2 times negative 2 squared. So negative 2 to the fourth is positive 16 minus 2 times negative 2 squared. Negative 2 squared is positive 4. So 2 times 4 is going to be 8. So we're going to get f of negative 2 is equal to 8. So let's see what f of positive 2 is, our f of b. So then we're going to get positive 2 to the fourth minus 2 times 2 to the fourth, second rather. So again, we're going to get 16 minus 8, which is equal to 8. So that third condition for Rolle's theorem is being met, so we know that there's an extrema value. So now that we know for sure that there are extremas in that interval, let's go ahead and find them. So to find extrema values, as just a review, you have to take the derivative and then set it equal to 0. So first we got to find that derivative, f prime of x. And since this is a polynomial, it's really easy to find the derivative. We're just going to apply our power rule. So taking the derivative of x to the fourth, we're going to get 4x cubed minus 4x. So now what we're going to do is we're going to set the derivative equal to 0 and solve for x. Okay, so when we solve this for 0, we don't want to just divide by anything. We want to factor it out first. So if you notice, 4x cubed minus 4x has a greatest common factor of 4x. So if I take a 4x away from both terms, I'm going to be left with x squared minus 1. So now I can set each of those things equal to 0 and solve for the x's there, because I don't just want to divide by x, because then I lose solutions. So 0 equaling 4x means that 0 is equal to x. And 0 equaling x squared minus 1 means that we should probably factor the x squared minus 1. We get x plus 1 and x minus 1. So if we set both of those equal to 0, we get that x is going to be equal to, whoops, not 0 anymore. We're going to get that x is equal to negative 1 and x is equal to positive 1. So now we just want to look and see if these are all in our interval or not. And our interval, if you remember, was negative 2 to 2. And all three of these values are in that interval. So we can say that the c values are plus and minus 1 and 0. So those are the three extrema values for our function. So there we go. So we have one more theorem to talk about today, and that is the mean value theorem. And the mean value theorem, or the average value theorem, mean and average mean the same thing, says that if we have a continuous function on the closed interval from a to b, and it's also differentiable on the open interval from a to b, then there's going to exist a c value, so an x value in between a and b, such that the derivative of c is going to be equal to f of b minus f of a over b minus a. So now that's a lot of variables and a lot of f's and all of that. Might be thinking, where does this formula come from? What is it really saying? So f of b minus f of a over b minus a kind of looks like y2 minus y1 over x2 minus x1, which is equal to the slope formula. So this just says that there is a c value in the interval where the slope at c is equal to the slope of the secant line. Now the secant line is just a line that connects 2 points. So we're going to draw a quick picture to illustrate what we're talking about. So we got our x and y axes, and say I just have this random function. I don't know what the function is, but we have a picture of it. And so say that we have a down here and b down here. So that means that we have f of b over here and f of a over here. So now if we draw the line connecting these two things, that's what we call a secant line. A secant line is just a line that goes through 2 points on a curve. So in other words, we can find a c value somewhere in between a and b that the slope of the tangent line at C is the same as the slope of the secant line between A and B. So it looks like we can kind of probably find our C value right here. These lines look like they're parallel to each other. And there could be more than one. So I could have a C down here. And it almost looks like I have one over here too. So we have like C1 and C2. So all the mean value theorem is saying is that if you find the secant line between the endpoints of your interval, that you'll have at least one C value in between those two endpoints, where the slope of the tangent line is equal to the slope of the secant line. That's all it's saying. So now let's try and use it. So we're going to use the MVT, or the mean value theorem, to find all of the C values in the interval from 1 to 4 for f of x equals 5 minus 4 over x. So, okay, so first we have to check a few things. Is the function differentiable over the whole interval? So, first, we should probably know if it's continuous or not. So is f of x continuous on 1 to 4? And the answer to that is yes, because we can plug in any value between 1 and 4 and not get an undefined term over here in the 4 over x. So that's a good check. So now we also need to check if it's differentiable everywhere. So if we take the derivative, can we find the derivative at every point in that interval? And the answer is yes, because we still won't be plugging in x equaling 0 at all. So our derivative will still exist everywhere. So those are just two things that you have to check off. Okay, so now we should probably find out what f prime of c is going to equal. So in order to do that, we need to find f of b minus f of a over b minus a. Okay, so f of b is f of 4. So we have f of 4 minus f of 1 over 4 minus 1. So if we plug 4 into our function, we're going to get 5 minus 4 over 4, which is 5 minus 1, which equals 4. So now I have 4 minus. Now plugging 1 in, we're going to get 5 minus 4 over 1, which is just 5 minus 4, or 1. So we're going to get 4 minus 1 all over 3, which is just 3 over 3, which equals 1. So this is what our f prime of c should equal. So we want to find out what those c values are. So to find out what they are, we should probably know what the derivative is. So let's find our derivative real quickly. But before we find our derivative, let's rewrite the function so it's a little easier for us. So 5 minus 4 over x is the same thing as 5 minus 4 times x to the negative 1, using that negative exponent to bring up the x from the denominator. So then now it's much easier to use our power rule of differentiation and find our derivative. So derivative of 5 is 0 minus 4 times negative 1 x to the negative 2, which is just going to be positive 4 times x to the negative 2, or 4 over x squared. Okay, so we want to find all of our c values. And we know that f prime of c equals 1. Well, f prime of c is also going to be equal to when we plug c into the derivative. So in other words, it's going to be equal to 4 over c squared. And we know that the secant line slope was 1, so we want to know what 4 over c squared is equal to 1. So now, if we multiply both sides by c squared to get rid of our fractions, we're going to get 4 is equal to c squared. Then if we move the 4 over, we're going to get 0 is equal to c squared minus 4. And then all we have to do is factor. So we get 0 is equal to c minus 2 times c plus 2, since it's the difference of perfect squares. So then we know that 0 is equal to c minus 2, 0 is equal to c plus 2, which is going to give us that c equals 2 and c equals negative 2. But we have to remember that our interval was 1 to 4. So we can actually cross off the c equaling negative 2 because it's not inside of our interval. So we have a c value of 2. So that means that the slope of the tangent line at 2 inside of that interval is the same as the slope of the secant line between 1 and 4. Okay, let's try one more example using the mean value theorem, and this time we're going to use some trig functions. So let's apply the mean value theorem to sine of x on the interval from 0 to pi. So we know that sine of x is continuous and differentiable everywhere, so we can just quick write up those. So f of x is continuous and differentiable. So those two conditions are being met. So now let's find the slope of the secant line. So we want to know what f of b minus f of a over b minus a is. So f of b is f of pi. So that's the sine of pi, which you remember, if you remember, is 0, minus the sine of 0, which is also 0, all over pi minus 0. So we get 0 over pi, or just 0. And that's the derivative at some c value. And we know that the c value exists because all the conditions for the mean value theorem have been met so far. So now let's find our f prime of c and then set it equal to 0. So f prime of x is going to be equal to the derivative of sine, which is just cosine of x. So now we want to know where f prime of c, or the cosine of c, equals 0. So using our knowledge of the unit circle, and we also want to keep in mind that we're only looking over the interval 0 to pi to find our c values. So cosine is equal to 0 at pi over 2, and that's actually the only place on the unit circle in that interval where cosine is equal to 0. Cosine is also equal to 0 at 3 pi over 2, but that's not inside our interval of 0 to pi. So we know that we have a c value at pi over 2, which means that the slope of the tangent line at pi over 2 is the same as the slope of the secant line between 0 and pi. So that's how you go about using the mean value theorem. So as a wrap up, when you use Rolle's and mean value theorem, you always want to make sure that you go through and check all the conditions for both before you go ahead and apply it. And then all it is taking derivatives and solving for c values. So thank you so much for watching. I hope this helped. Have a great rest of your day.